As a program chair this year, I would like to dedicate this day to our reviewers. You heard Oliver Brock yesterday evening. He talked about how much RSS welcomes the involvement of the community and how much it seeks the involvement of the community, and definitely reviewing for RSS is the first step to get involved. This year we had 287 reviewers who provided amazing reviews for us. I'm thankful to each and every one of you. We obtained a total of 617 reviews. So we try not to overload. We tried not to overload people, but on the other hand, we ask you to do the reviews yourselves. And it's a huge effort. We've all done this. We understand how much energy and time it takes to provide a good review, and we all like to. It's wonderful if we could all provide the kind of review that we would like to see. And this doesn't mean a harsh review. This means a review that is constructive and helps every one of us. We had, as I told you, an AC meeting at RISE, and at the end of the AC meeting, I asked each of the AACs to identify their best reviewer. So this is by no means a bulletproof process, right? There were many reviews that have not been, excellent reviews that have not been, that are not in this list. This is the list that I got from the area chairs. And I asked all these people if they wanted to chair an RSS session, and many of them are not here. Some of them, however, are here, and they will be chairing the sessions today. So we are going to start. We are going to award actually 3 Best Reviewers Award tomorrow at the closing ceremony. And as I said, some of these people are around and will be chairing the sessions. We are starting with Tim Barfoot from the University of Toronto in Canada.
Okay, good morning. I'm Harry Asada from MIT. My student Faye and myself came up with a really cool idea of a robot design that you have never seen. Here, a pair of robot fingers attached to your hand. So you have 7 fingers instead of 5. So imagine you can do some clever things with the 7 fingers. Well, soldering is one thing, you need more fingers. And awkward work like this, or task needing 2 persons can be streamlined. If you have a hard time in the fingers or lose a hand, we can help you. But traditional method is just using very simple ones or complex ones for total replacement. Our approach is to take the existing hands and then provide a robot that to complement the human movement. And we enhance the functionality of the healthier hand. You know how difficult to open it, like this? We focus on this paper on the grasping. Grasping is the most fundamental part. We explored many objects to grasp, and we did find that the 7 fingers have a very strong correlation among them. They don't move independently. Following some the functions. It resembled the posture synergies and the neuromotor the literature, and we hypothesized that there exists the synergies even for 7 fingers. So because of the synergy, we must be able to control these robots in correlation to the actual hands you can measure. So we took a lot of data, 20 objects, 5 trials, including 20% validation data. And what you know that the Santero's famous work, 2 principal components of finger postures can explain the 80% of the task. One is actually opening and closing in face, or the second one is kind of a twisting actions. Interestingly, even though you have 7 fingers, we did almost exactly the same results. So first one is just open, close in face together with the robotic fingers, and the second one and the third one. If you add all of these, you get the 85% of the recovery. So because of the synergies, we should be able to control these robot fingers in correlation with the human hands. So we'd like to find the control algorithms to control these. And doing this, we first put all the human fingers data into input data space, and then robot fingers postures in output space. We try to find the functional relationship between the two based on the partial least squares. So this is really data-driven method. So if you think about the unit vectors in two spaces, input and outputs, you can find a specific direction that you see the highest correlation between 2 sets of data. And you can repeat this process to get the second highest correlated directions and the third relations. And it just you can reduce the huge input space into just a few modes. The first mode shown next is just similar to open and close of fingers in phase, and so did this a set of robotic fingers. Second one is a little bit twist motions, thumbs and the forefingers out of phase, so that this robotic hands. Adding the one more component, we can actually approximate almost all postures in a very high accuracy. So to implement this, to control the robot, you need sensors to measure your fingers. Remember that you need only 3 principal components, so we need just 3 sensors. And then expanding that one to 6 DOF finger motions, you can actually drive this in correlation to your hand motion. So the first one, this is the first mode, and this is the second principal component. By linear combinations with these, you can generate all kind of a grasp. So you can just naturally grasp it, and then robot fingers follows. This is a very natural way you prefer to grasp things in this way. It's very, very natural, implicit. You don't need to command the robots how to grasp it. Well, actually, based on this, we're exploring interesting applications. If one hand is busy, you can just do this, or you can open the lid, or you can actually manipulate the screwdriver. Even though you have one hand, you can work in a factory. So we propose a supernumerary robotic fingers, and we propose the synergy-based controls. You can control this. Our future plan is to bring in some sensors, or optimize some mechanical design, and this can actually expand current work to many, many directions with so many interesting ideas coming out. So please join us to exchange more ideas. Thank you.
Yes, I'm Eric Diller, and I'm at the University of Toronto. I'm going to tell you about some work we did while I was at Carnegie Mellon University involving the control of magnetic microscale robots. These devices at the tens to hundreds of micron size scale are appealing for their potential to give us direct access to tiny confined spaces. And we heard a lot about this earlier from Brad Nelson. But we're interested in applying these microscale robots for applications in the manipulation of microscale objects, as shown on the right, where one of our robots is manipulating some objects in an assembly task. We're interested in deploying them as mobile sensors in a distributed network, and of course for healthcare and bioengineering applications, as we heard about earlier this morning. Magnetic actuation has emerged as a preferred wireless power and control technique for mobile magnetic microrobots due to the capabilities for long-range operation using a coil system like the one we have here on the right. Magnetic fields can work in most environments, and they can penetrate through most working materials in our environment. We can also apply relatively high torques and forces to our magnetic microrobot body. Brad Nelson already introduced these same equations here, where we can apply magnetic torque T, which acts to align our microrobot, which has magnetization M, with the applied field B. And our force is pulling our magnetic microrobot along field gradient directions. And of course, these torques and forces are related linearly to the currents through all of our coils. This has allowed us to design a lot of different motion techniques for microrobots in the community using magnetic fields, including helical propulsion, crawling or rolling motions, levitation using magnetic field gradients, and even biohybrid actuation, which is exploiting some of the useful motion of microorganisms. However, a critical limitation with this magnetic actuation is that we can actually only achieve 5 degrees of freedom motion in actuation. And that is, we're lacking the creation of a torque about the magnetization axis. So this video illustrates the 5 degrees of freedom we can achieve, forces in any direction, and we can create roll and pitch torques by rotating the magnetic fields. But no matter what fields or field gradients we apply to this magnetic microrobot, which is modeled as a single magnet, we cannot create this rotation about the yaw axis, or the magnetization axis. And of course, this is going to limit how we can implement this for sophisticated microrobot applications, with microrobots moving in 6 degrees of freedom. One way we can get around this issue is to simply design our microrobots to be axisymmetric about this magnetization axis. However, for more sophisticated applications, such as what we have on the right, which is one of our magnetic microgrouping robots, which is trying to assemble objects in 3 dimensions for more complicated assemblies. In this case, we're building a 4-bar assembly. Of course, we're going to need full 6 degree of freedom actuation to achieve dexterous operation and high-speed operations with this type of task. So, we can easily achieve rotations about roll and pitch axes using applied magnetic fields. And we can create forces in any direction we like using field gradients. Our unique contribution in this work is to achieve the 6th degree of freedom actuation. We do this by relaxing the assumption that we have a single magnet magnetized in a uniform direction. One way we can do this is to add additional magnets to the side of our primary magnet, which are pointing in a different direction than this primary magnet. We can apply field gradients to pull on these side magnets in certain directions, which will induce a rigid body torque about our entire microrobot body. And by choosing the direction these side magnets are oriented, we can induce this torque about any axis, including about the primary magnetization axis, which is the actuation which we were not able to achieve previously. We can do this without interfering with the original 5 degrees of freedom, as shown in this video. So we can create forces in any of the 3 directions, the same as before. And we can create roll and pitch rotations using uniform magnetic fields. Now, to create the 6th degree of freedom actuation, we use field gradients to pull on these side magnets to create this rotation about the correct axis. Thus, we're achieving 6th degree of freedom actuation with a slight increase in the complexity of our microrobot device. But critically, we can do this with no increase in the complexity of our driving magnetic coil system. So we can implement this type of control in any driving system which could previously achieve 5 degree of freedom actuation. At the interactive session, we'll give some additional details of how we've experimentally validated these new control results. We've investigated some interesting arrangements of discrete magnets which lead to reduced coupling between the applied forces and torques on the body in a simpler mathematical description. We found a solution for arbitrary magnetization profiles for permanent or non-permanent magnets. And we've designed some sufficient conditions which a microrobot designer can use to ensure that their design will achieve full 6th degree of freedom actuation. Thanks, and I'd like to thank our funding through the NSF National Robotics Initiative Program.
I'm Art Mahoney, and I'm going to be describing some work that I've been doing at the University of Utah with Jake Abbott on 5 degree of freedom manipulation of an untethered magnetic device in fluid using a single permanent magnet. When I say 5 degree of freedom control, what I mean is the ability to wirelessly move a capsule, in our case, in up, down, left, right, forward, back, and pitch and yaw degrees of freedom. The application that we're really interested in is capsule endoscopy of the human body, where a patient swallows a wireless capsule camera, and we manipulate it through the body using externally applied magnetic fields. Our experimental setup consists of a single permanent magnet that's maneuvered around in space by a commercially available 6 degree of freedom robot arm. We have a localization system, in our case we use 3D vision, to always measure the position of this capsule in space. The experimental setup is shown on the right in the bottom corner here. The green capsule is the device that we're actuating. All of our components are commercially available, and you can get the permanent magnets from a hardware store. Now, this is a somewhat complicated slide that describes some pretty simple principles. Basically, the idea being that if you take this untethered device, place it inside of a magnetic field, a torque is produced, which makes that align with the field, just like a compass needle. In our case, the field is this dipole-shaped field that's generated by our external permanent magnet, the one that's held by the robot arm. To adjust the capsule's heading, what we do is we adjust the direction of this dipole field. Now, inside of a dipole field, a magnetic force can also be produced. The total force that acts on this capsule includes this magnetic force plus the capsule's weight. To control its position, we adjust the total force. Now, our system inputs into this whole manipulation system are the joint configuration of our robot manipulator. The system outputs are the total force applied to the capsule and this field heading. Now, the mapping is nonlinear, and so what we've done is we've used a resolved rates method to implicitly invert the problem. We've also applied some constraints that I'm going to be describing later, which introduce some really interesting functionality. We implemented a PID controller that performs closed-loop control over the capsule's position. In this case, you see, using feedback information, I should say, from our vision system. Over here on the left, you see an example of keeping the capsule's position approximately constant in space while adjusting its heading. At first, the heading goes from being pointed straight up to being pointed straight to the right. One interesting thing to note here is that the actuator magnet isn't always positioned directly above the capsule. In fact, it moves over to the left somewhat, as you see it doing right now. This is a non-intuitive result that we weren't expecting, but it's really purely due to the geometry of this dipole-shaped field. The non-intuitive nature of this problem really lends itself well to a robotic solution, we believe. Over here on the right is an example of keeping the capsule's heading constant while adjusting its position. In this case, it follows a square U-shaped trajectory where it first moves down, to the right, and then up. Again, notice that the actuator magnet isn't always directly above the capsule. You can see the cameras used for our vision system in the back. So in the previous examples, we did independent control of position and heading. In this case, we're actually doing simultaneous control to follow this remote center of motion maneuver, which could be used to visualize a single point in space from multiple different views. Now, we recognize that our vision-based localization system isn't really clinically relevant in the sense that if you have a capsule inside of your body, you can't really visualize it with cameras. Fortunately, there are localization strategies that exist. However, they operate at much slower frame rates. So we tested our methods, and we found that we can actually get down to localization rates of 30 hertz and still maintain pretty reasonable control of our capsule. The results are shown on the right. This is really good for us because there are current clinically relevant strategies that operate at faster than 30 hertz, so this is really good for us. We think this really strengthens our argument that these types of technologies can appear in a clinic in the near future. Again, notice the non-intuitive behavior of that actuator magnet. Now, there aren't any singularities per se in the magnetic field, this dipole-shaped field. However, singularities in the robot manipulator can actually introduce themselves as singularities in the entire manipulation system. What we've found is that we can, if we sacrifice control of heading near these singularities, we can actually maintain control over the capsule's position. We do this by imposing some constraints on a resolved rates method. This is demonstrated over here on the left, where that capsule still follows that same U-shaped trajectory. But notice that the manipulator is in its spherical rift singularity. In this case, we don't have very good control over the capsule's heading, but as you can see, we still have pretty good control over the capsule's position. On the right is an interesting example where the capsule is tasked with just levitating in space. The manipulator starts in a configuration where it's in a singular configuration. The user commands an input that ordinarily would require really fast joint motion, but what you actually see is our resolve rates method just naturally handles the user's input while minimizing the joint motion, and it also keeps the capsule in control. So please come visit my poster or definitely read our paper. Thank you for your time.
Okay, so good morning, everyone. My name is Stephane Bonardi. I'm from the Biorobotics laboratory at EPFL in Switzerland. And today I'm going to present you the work we did on learning locomotion for self-configurable modular robots. So self-configurable modular robots are robotics units that can attach and detach from each other in order to create more complex structures to solve complicated tasks. So they can adapt to the environment dynamically. And here the situation we envision is that you deploy a group of robots in the environment, and they have to perform a time-critical task. And during this task, they encounter an unknown event, for example, hardware failures, and they need to change the shape and to relearn how to locomote. We are making two assumptions there, is that the shape into which the robot reconfigures is perfectly known, meaning that we do not have to relearn the morphology of the robot. And also, it was not a shape that we previously know, meaning we cannot use a lookup table in order to find the new control parameters for the locomotion learning. And this is the technique I'm proposing is to quickly relearn those parameters. So here the strategy we are adopting is that we will try to detect and to identify bio-inspired patterns in the structures, like, for example, the body, the limbs, but also relevant articulation, like hip, spine, ankles. And we'll combine this information with symmetries in the structures in order to converge, to create a reduced control network that will allow us to converge. It will increase the speed of convergence to one acceptable solution. So the platform we are using to test our hypothesis is a robot self-configurable modular robots. It was developed at EPFL. So it's a robot with 2 degrees of freedom, as you can see on the right. It has a 4-way symmetric connection mechanism. And we use central pattern generators for the control of locomotion. Central pattern generator are a network of coupled oscillators. So I'm going just to show you an example of a test case that we envisioned to explain you the method. So here we took 5 modules that we connected into quadruple-like structures. And one of the leg modules is connected differently to the main module on the centers. So the corresponding control network here, the fully open case, that will be our baseline, is composed of 1 oscillator per degree of freedom. And each oscillator has 2 parameters to optimize. The first one is the amplitude, the second one is the offset. And here we consider nearest neighbor coupling, meaning each oscillator is coupled to its nearest neighbor. And we have to optimize the phase difference between them. So here we end up with 15 degrees of freedom for the structure, and 44 parameters to optimize. Now we are going to apply our method to this system and identify the main body of the structures and the 4 limbs. And we reduce the number of parameters to 21 parameters to optimize with 7 degrees of freedom this time. If we further apply the symmetries to the structures, we can share amplitude and offset for the 3 legs, 3 oscillators that correspond to the legs that are symmetrical. And we further go from 21 parameters to optimize to 17. Finally, we will apply symmetries to the fully open network, and we go from 44 parameters to optimize to only 30. And we'll compare all those different approaches and optimize them. And here you can see the results. So for the first few iterations, our methods, so body limb finder symmetry, and pure symmetry, completely outperform the fully open case. And so what we can show on the histogram and also on the curve, but this tendency tends to weaken as the number of iterations increase. So here is an example of the results that we obtain. And you have to keep in mind that we are in a time-critical situation. So we cannot wait for the full convergence. And here, for example, 5 iterations cost 1 minute of optimization on our clusters. So meaning at full convergence, which corresponds to around 800 iterations, it's almost 3 hours of computation. So, and here you can see that the tendency weakens a bit between the different approaches. So the take-home message is that here we are proposing an algorithm to automatically detect bio-inspired patterns and symmetry, and to use those information in order to provide the reduced control networks that will significantly outperform the fully open approach in the first 30 iteration by a factor of up to 10 iteration. So thanks a lot for your attention. If you want more information, please come see us at our poster E4. Thank you.
Hi, I'm Matthew Piccoli from the University of Pennsylvania, and I'll be talking about cogging torque ripple minimization, or what we call anti-cogging. Lots of robots require high torque, direct drive, or low gear ratio actuators, such as human-safe back-drivable robotic arms, haptic devices, and high-fidelity position control. But the motors in robots tend to be expensive. Why use motors like this when there are motors that are rated to the same torque, half the weight, and a third the cost? This motor should run smoothly, but it doesn't because of torque ripple. Across a wide range of motors and electronics, torque ripple and cost are inversely related. Here on the x-axis we have cost, and on the y-axis is the torque ripple ratio, which is a measure of torque ripple, and you can see that cheaper motors have more torque ripple. In these applications, computation electronics often hold a large portion of the cost, but with Moore's law and consumer electronics continuously driving down prices, actuators become the dominant cost, relatively speaking. Let's look at the 3 main sources of torque ripple to see if we can help this situation. Mutual and reluctance torque are when current flows through the coils, causing a magnetic field that reacts with the magnetic fields in the rotor. Ideally, the shape of these currents with respect to the motor position should be sinusoidal or trapezoidal to make the motor spin, but in reality they aren't, and this shape discrepancy causes a torque ripple. Voltage and current sensors can measure this discrepancy. Cogging torque, also called detent torque, is when the permanent magnets attract the motor's core. Unlike mutual and reluctance torques, cogging torque cannot make the motor spin continuously, only contributes to torque ripple, is always present, and is only detectable with mechanical sensors. Torque ripple has been heavily studied in the last 25 years, and most of the research falls under 2 categories: software methods for mutual and reluctance torque ripple minimization, and hardware redesign methods for cogging torque ripple minimization. But can we combine these 2 philosophies to minimize cogging torque ripple with software? Holtz and Springab laid down the foundation for cog mapping by iteratively monitoring current, while a speed loop tried to hold speed constant. We extend this to 2 methods without requiring a speed controller, a current sensor, or iteration. The first method is to use position control at every position and map the applied voltage or current when the motor is stopped. We can also compensate for static friction or stiction and transistor dead time with this method. The second method is to spin open loop as slowly as possible and map the accelerations. You can see these 2 maps agree nicely with each other, but to double check, we used a force torque sensor during testing to validate the 2 methods. Now, we can invert the cog map and feed forward these torques, currents, or voltages. We tested both methods on 11 motors. This is the same graph as before with price versus torque ripple ratio, but now with the anti-cog motors. You can see what was once an inverse relationship is now roughly constant with an average of 69% reduction. We think PWM resolution is the cause of this constant. You can see peak-to-peak torque ripple is on the same order of magnitude as the PWM resolution, between 1 and 5.5 counts. So we doubled the resolution. A motor that had 69% reduction went to 82% reduction simply by doubling the resolution. To verify that anti-cogging works in robotic applications, we made a robotic arm modeled after a Phantom Omni. We looked at the motors with a torque rating within a factor of 2 of the Phantom Omni's continuous torque, then ranked them by performance and economic value, which we defined as the inverse of peak-to-peak torque ripple times cost. The naturally smooth E-flite Park 400 has the best value, but after anti-cogging, the naturally rough Exceed RC Rocket 400 had about the same peak-to-peak torque, but only cost a third and was the cheapest tested motor. We used an updated motor driver with an even higher voltage resolution, as well as wireless communication, so that no wires cause friction by crossing over the joints. We ran the arm along various trajectories, including this 36-line segment, 2-meter trajectory, where the arm has a root mean squared error of 7.4 millimeters without compensation, while with compensation, the error was 3.5 millimeters, which is a 52% reduction. We brought demos. Both motors from this arm are on display during the interactive session, so you can feel the cogging torque with your own hands and then feel it disappear. We also have a handful of other motors, so you can feel the difference between expensive and cheap motors. So here's anti-cogging turned off, and here's anti-cogging turned on. And here's the desired trajectory along with the same 2 paths generated with encoder values. As you can see, you can now get good performance from really cheap motors. Thank you, thanks to our funding sources, and thanks to everyone that worked on this project.
Art, I was wondering, what media were you in with those capsules? What were they?
Yes, that's water.
That's water?
Yep. The reason why we want to use water is because it's a common medium used to basically expand the human stomach during current procedures. Yep. Say that one more time.
Siemens wasn't able to demonstrate that with their system. That's great.
Yeah, that's exactly right.
Yeah, yeah, good.
More questions? There's one over here. Can we get a microphone down there?
So this is for Eric. When you're modeling your system, do you just model all the forces as dipole-dipole interactions, or do you do any sort of near-field modeling?
So the traditional way to model a microrobot is to consider it as a single dipole, and then the fields from the external coils are assumed as uniform fields. So if we have a dipole assumption, then it's a great assumption to make. In our case, with the distributed case, if we have discrete magnet elements, we can treat each one as a single dipole and do the modeling that way. Or we can do a continuous integrating forces and torques over the entire volume for more precision.
Still got lots of time for questions. There's one down here.
This question is for Harry. Why 7 fingers? Why not more or less?
What a good question. Just kind of, compromise. But I know best explanation is that we have kind of 2 groups in 5 fingers, thumbs, and the other 4s. And we'd like to expand the functionality for each side, and so that naturally, becomes 2 more. So the one finger is very much correlated with the thumb. The other fingers is very much correlated to 4. And then with 7 fingers, we can create most of the foam closure type of stuff, which is very stable. And also, 2 fingers can hold something while the other human fingers performing something else, which is very, good things we can do.
Also a question for Harry. So you showed that you can move these 2 additional fingers more or less kind of following the motion of the human fingers. There might be situations I can imagine where you want them to move more independently or more task specifically. Is there a way to control them in that way too?
Yeah, that's excellent question. So what we talked about is grasping, and the 7 fingers grasping. And so Synergy is a sort of a baseline, default or lowest in the hierarchical, control structure. And if something specific, comes in, it pops up to some other behaviors comes in. For instance, while holding this, you want to do something else, which is a future research issue.
Ed's got a question down here.
So for Matthew, E5, it sounds like that you're basically calibrating a lot of the performance of the motor. Is that calibration stable over time? Do you have to recalibrate the motors every 100 hours, or?
So this is a function of the internal of the motor, and that doesn't really change as you use it unless you use it improperly. So if you melt it, for example, the magnetic field of the magnets will degrade and the coils will kind of melt together. But if you drive it properly, there's nothing about the motor that should change except for maybe bearing wear. So we haven't hit that point yet, so we just use the same calibration for a really long time.
I think we still have a couple minutes. There's one over here.
For E5, along the same lines as that previous question, have you thought any about the effects of water on operation? And just want to confirm, you're not sensing anything about the motor, right? This is open loop?
So the sensing that we do is just with a position sensor, which you already need for servo control. And water, we certainly haven't thought of it. Brushless motors do work underwater as long as you keep the electronics out of it. The characterization assumes that there's no friction or external forces on the motor as you characterize it. So it would be recommended to characterize it outside of the water and then put it in the water as opposed to characterizing it in the water.
Any more? I've got one for E4, just in the interest of sharing the questions around. So I noticed most of the robots you were dealing with could sort of be described by a tree structure. What happens when there's a loop in the morphology?
So we can also deal with that. So we did some tests. In fact, here I only presented one. We did one with a big cycle in the structure. So it's completely possible, but here we are considering the cycle as fixed, in fact, to simplify the modeling. And also to reduce completely the number of parameters to optimize.
Thanks. Just 1 minute left. Any more nagging questions? All right, let's thank the speakers again.